All right, let's take a look at the final challenge here. You can see that you're given an IP address with a port number associated with it. And this website pops up called Простоквашино, which is actually a fictional name in one of the Russian nice cartoons. You can actually look it up on YouTube. There are some funny things going on there. So in any case, it's a real place in the real world to share real knowledge. And for obvious reasons, you can post things to share that knowledge, right? You can also see that there are some users already existing, some popular tags that actually don't really have any kind of popular tags, but you can have it. There are some likes going on. And there are also some links in the front end and back end. So your goal was technically get into the account. I have this user, and you most likely recognize this name, right? From a recently born baby. And you can also notice that this user has this post, which you can see that I'm not logged in yet, right? So everybody can see the post. It's all public, some kind of implementation of RSA taken from this link on GitHub. And you can see we did some tweaks here. Right, specifically, I'll show you later on what exactly I did. But in any case, you can see there is a very common implementation of RSA with a few bugs, and those bugs are the ones that we're going to try to exploit. If you're not sure what RSA is, you can look it up. It's a Rivas, Shamir, and Edelman encryption algorithm that allows you to use a public encryption in which you have a public and private keys. Public key is typically shared with everybody, technically speaking, with the whole world, and private key is always kept secret. That's the reason why it's called private. You can encrypt with one and decrypt with the other. Doesn't matter which one you pick for encryption or decryption, right? As long as you keep the order. If you encrypt with a public key, you have to decrypt with a private, and vice versa. In any case, this algorithm is relatively long. However, we don't have to really dive into details how it works. All we have to do is recognize that there are two functions called encrypt and decrypt. Right? Apparently, these functions unpacking some stuff and potentially returning some kind of keys, right? Or maybe not. You can see that keys actually involved in it. So most likely it doesn't return the keys, but maybe it returns something else, and then you will figure out, or most probably is going to return you ciphertext, right? Given the plain text, which is why it's called cipher here. And on the decryption side, you can notice that it's taking a ciphertext. It takes a pair of two numbers, key and n, and later on it uses those numbers to actually decrypt this into a plain text. In any case, you can notice that to generate all these keys and then encrypt and decrypt, you have to call a getPrimes function. Apparently, it returns the PQ numbers, and if you look up RSA, you will know exactly what those are. Those are prime numbers, quite commonly very large. And later on, you will notice that there is a function called generate key pair that actually takes those P and Q in and provides an output of public and private keys, which are later on used in encrypt and decrypt for testing functions. So it's a relatively straightforward algorithm in terms of this main function, right? It's a bit complex here. But regardless of this, let's take a look what's happening with the account. Well, we can't really do anything, right? It doesn't seem like it. If you try to maybe sign up and create new accounts, maybe unfollow somebody, post things, all those XSS, CSRF attacks should not work, hopefully. And eventually you will realize that maybe that's not the way to go about it. And we did have a hint that GitHub has lots of answers, right? You can notice that backend and frontend links are here. So let's open them up, and they do in fact lead to two GitHub repositories. You also will see that this repository is apparently called React Redux Real World Example App, and it's forked actually from a React Redux Real World Example App, right? That actually exists right here. You can notice that the latest update was just a few years ago, but for this repository that was forked, though this address was just a few months ago. So something did change here. Same applies to the Flask real-world app. So this is a Python-based app that is a backend, and this is the front end, right? You can see that all the README, all the things on Java npm install, everything kept the same exact way as it was originally. So what has changed? Well, not many people realize, but developers do post accidentally passwords, credentials, keys to cloud providers, maybe AWS keys, or maybe just a key to their own repositories on GitHub, maybe keys to some kind of applications that they're running locally, and maybe even already publicly available on the internet. In any case, sensitive information getting published every day on GitHub. The question is, how do we detect this, right? And then the other question is, can we actually use that? For obvious reasons, we can use credentials if we find them. That's the best part of it. And also there are tools that actually allow you to look up this kind of stuff automatically. You just feed it the repositories you want it to scan, and it's gonna look through what we're gonna call commits. Commits represent every single change that developers decided to tell other developers that they have made, maybe even to themselves. In other words, sometimes it's a bug fix, maybe adding a new feature, maybe a small fix, maybe a typo fix, or maybe just writing code and slowly and steadily they're developing the app, and they want to have this timed, right? Everything is timed. So you have a timestamp, you have a user associated with every commit, and every commit represents a snapshot in the development cycle of this specific repository or application. So let's take a look what kind of commits we have, for instance, on the back end as well as the front end. So this is the back end, the front end was already opened. You can see that on the back end, I actually only made one commit. Block specified user from editing anything. You can click on it and you can see exactly what was changed. So you can see that if somebody does log into this user account, they will not be able to change anything. Apparently, there are some tricks here and there. We don't have to dive into too much detail here because it doesn't really relate to any credentials. Apparently, it doesn't leak anything, right? So there is nothing, just a few statements added. Let's take a look at the front end. You can see there was bug fixing, there is email adding. Oh, wait a second, email adding. Well, if you try to sign in, it actually asks you for an email instead of a username, right? So let's take a look, what's that email? Apparently the email is elon@musk.com. So we're gonna copy that over right here. And we're gonna move on, right? And notice that I actually added this so that I don't forget about it. So I move on and updated header, footer, blah, blah, blah. And you probably already noticed that I actually was removing password for security reasons. Well, developers also don't realize that every commit that they publish is actually publicly available as long as the repository is public. So you can't just say that I'm not going to delete my previous commit. I'm actually going to create a new one and fix the error. So apparently here, I removed password. There is no password anymore. Maybe there is. But you can notice what was removed with minus signs, right? So this thing was removed. Apparently a password for this user would be made for real cool names. And you can also see the commit before it, which was adding a password that adds those lines here with the plus signs, right? So you wouldn't have those later on this commit, for instance. At footer, you would no longer find it. If you take a look at the whole code of, well, this is a code for index.html, but if you take a look at the code for that specific file, you would not be able to find that password in most latest commits. So let's come back here. We're going to paste it and successfully sign in, right? So we got into the account. And now finally, we can actually take a look at the account by clicking on this button. And lo and behold, we have some information, encrypted information. And apparently this user can actually code, even though he has just been born. You can notice that this information is pasted in the, I don't know, whatever field it is, right, description field, as an array of numbers. So I'm going to copy this stuff. Right, you can try to change anything, but it won't work because in the back end, that user was actually blocked, right, from editing anything. So in any case, that's all we had to do for now. Now we come back to our feed, right, the original article that we had here. We're going to paste it to our favorite editor. In my case, it's Visual Studio Code. And we're going to take a look at this code, try to analyze it, and find a way how to insert stuff that represents an array to just test it out and maybe play with it, maybe try to even hack it, right? So I'll go to actually break that code. You can notice that there are lots of comments here where they're needed. There is testing if a number is prime. Maybe it's sufficient, maybe not. Who cares at this point? We're trying to figure out what's happening on the side of math. Well, to be honest, thankfully, we don't even need to get into the math of RSA. What we need to realize is that it was based off this GitHub repository. And in fact, you can open it up and it's still there. You can compare line by line. You will notice that there is this difference in a get prime, specifically get primes, not prime function. And you can notice that all I did here is creating a random number generator. I'm seeding that number with another random number from 0 to 30. And based on that, I'm going to, based on that seed, right? I'm going to randomly generate numbers from 20 to 1000, check it if it's a prime or not, and then continue on doing this over and over and over again until it actually spits out two prime numbers. Is it efficient? Not really. But again, our goal is to figure out how to break this inefficient code. Well, let's think about this. I'm going to open a Python interpreter, right? And I'm going to say import random. And now we're going to take a look at just random dot. We're going to just copy literally what it said here, in fact, right? And I'm going to do exactly the same thing. Rand.randint from 0 to 30. I'm going to repeat this line over and over and over again. You can notice that all these numbers seem random from 0 to 30. In fact, they are called pseudo-random number generator, right? This random thing. So these are pseudo-random numbers, and they look random. Sometimes they repeat apparently, but sometimes not. And quite often you can see that you're going to get a prime number, right? It's like 17, 5, 23. So in any case, what's the point here though? Well, the point is, if we know the initial number that was fed inside of this seed function, Python will actually start generating pseudo-random numbers that are predictable. What does that mean? What do I mean by predictable? Well, we'll take a look at another Python interpreter. In that interpreter, it's a new one, right? We're going to do the same thing. And you can see that these numbers don't really correlate with the numbers on the left, right? So numbers on the right don't correlate with the numbers on the left. Well, can we do better? Can we actually make those correlate? In other words, predictable. So that if we want to have a sequence of, say, I don't know, some kind of sequence of numbers, we can replicate the sequence over and over again. Well, in fact, we can. This is called seeding random number generator. So if you feed to that seeder a number, just let's say 77, and then you're going to try to generate those numbers, you can actually do the same exact thing anywhere else in the whole world, not even on this computer. Right? We're doing it right now at this computer, but technically speaking, you can try it at home and see what happens. My insert mode was turned on. All right. Notice 25, 8, 10, 6, 7, 6, 26, 30, right? Exactly the same sequence. And you can continue on. I can predict right now. I'm going to be a, what we call in Russia, Baba Vanga. So 17, right? Next will be 19. Boom, there it is. So in any case, it's predictable. And for this reason, whenever we are generating two prime numbers, P and Q. We're going to know exactly what sequence was used to generate those numbers, right? So all we have to do now is to figure out what number was originally fed inside of a seed number, and then we're going to generate exactly what P and Q were when this person actually was generating and encrypting. So in any case, how do we do this? Well, there are a few approaches. You can just literally rerun this over and over and over and over and over again until you actually can decrypt this into what resembles ASCII codes, right? An ASCII table is our English alphabet plus some other characters that are very well known and available also on your keyboard, most of them. But regardless of this, how else can we break this? Because if we just wrap it around a random for loop that just infinitely generates it, maybe it's not going to generate all those 30 numbers within a reasonable amount of time. Or imagine that you have from 0 to 3 million, then it's going to take forever, right? Maybe it is better this time to actually use something that more linear, starting from 0 until the very end. Yes, it will take long, but not as long maybe as this random number generator would take. So what we're going to do, we're going to copy this get primes, right? And we're going to call this a hack message. We're going to see that we're passing an array. And inside of this hack message, and the reason why we're passing an array, I'll show you exactly why. You can see that decryption is happening on the key, and you pass a ciphertext to it, right? So the plaintext based on ciphertext and key using some kind of math, right? We don't even need to worry about this. If you took a look at it, it's great. If you didn't, that's fine. What's most important is this little code here, line 103. We are getting a character from a ciphertext apparently, and then we're going to multiply, or actually it's putting the power, right? Double multiplication sign. It's not multiplication. So you put a power of to the power of key, and then %n means that you take a remainder from a division by n. And then you convert it to a character in ASCII. Later on, you're going to spit it out as a result. So apparently this is actually taking a number, right? You cannot just take a character and put it to the power of something. Actually, it has to be a number because only numbers are divisible, multipliable, right? And put into the power of something. So key is a number, so character has to be a number. So in other words, this must be an array of numbers. And this code doesn't tell us, but we kind of can predict it. And if you didn't figure that part out, potentially you could actually take a look at decryption here, right, in the given code that was available on the website. There was a main function here. And that one is telling you that encrypted message was the encrypting message with a private key, right? Your message is, but when you encrypt, where is encryption? There is encryption. When you encrypt stuff, it's going to spit out the encrypted message. So if you run this code as is, right, that asking you to enter this message, and then it encrypts this message, you're going to see that it spits out an array of numbers. And then when you feed that array back to the decrypt, it actually will be able to decrypt. So that's how you can kind of figure out that it takes in an array if you didn't do it otherwise. In any case, all I have to do now is to say, do this, right? I'm gonna comment it out, and I will run the hack message thing. And coming back to hack message in a second. In a hack message, we are wrapping around our get primes with a for loop that starts at 0 and ends at 30 inclusively, right? Hence the reason why we have 31, because in Python, the range will take in the first number inclusively, but the last number exclusively. And then we're going to feed that number to the seeder in the random number generator and just randomly generate those P and Qs. And as soon as we did generate those, we're going to continue generating the P and Q. Sorry, not P and Q, private keys based on P and Q. And because we don't care about the public key, or we care about the private key to decrypt. The reason why, because it was actually in this code here, we use the public key. Even if you didn't figure that one out, you could try to decrypt with both and see what happens. But in our case, we use a public key to encrypt. So we're using a private to decrypt. And because we don't need it, in Python, you can just emit a variable by putting an underscore if you know that it is getting returned by a function. And then you put in here try except just in case if something breaks. And we're trying to decrypt this message and spit it out on our screen, right? And we're doing over and over and over and over again. So let's try to see what's going to happen. And all I have to do is run this break RSA. And technically, I actually have to tell it what to break, right? Before I actually break it. So I'm gonna copy it again, just in case if my clipboard got messed up here while I was messing around with the code. So I have a hack message call that takes in the whole array of numbers given inside of the account. And now we're gonna see what's gonna happen. This linter is definitely gonna take some time. You can notice that it will actually take some time. And as it starts decrypting it, it's gonna spit out these random characters. Eventually it will do it. So we'll just wait for a bit and see what happens. And as you can see, we actually got our hit in several minutes. And on the 7th, I believe, or 8th iteration, I think when I was 7, so maybe it's an 8th iteration, this is our answer, right? Everything that it was trying to decrypt as was gibberish, unless you can read some Chinese characters here. And you can see that it's in a recent article about exploiting almost every antivirus, the writers mentioned a very well-known test string that is used in a Windows POC or POC that stands for proof of concept. What is SHA-256 hash of the test string? So it's a little bit of OSINT, right? Open source intelligence. And to do this, we'll just look it up and it just keeps going. It's probably gonna take overall, in a worst case scenario, if it goes all the way to 30, it's gonna take about probably half an hour. So we'll copy this over, right? Exploiting almost every antivirus. Go to DuckDuckGo, or maybe Google. I'll try DuckDuckGo first. With my antivirus, depending on which you like your privacy or not. And we'll take a look at the very first hit. You can notice very recent article in April 20th, right? Exploiting almost everyone. You can see Bitdefender, Kaspersky, Webroot, right? All the very commonly known antiviruses, and Kaspersky, Bitdefender constantly top it in terms of detecting stuff. There is a very nice way to actually bypass them and try to exploit. There is a proof of concept. And what string they use to do this proof of concept is actually called an ICAR, right? And you can notice that it's actually printed right here. It's echoing right inside of something. But if you say didn't notice this, or maybe kind of try to figure out what the heck is this, just looks absolute gibberish as well as that code here. So how about we look it up? What is this test string? This was another hint, by the way, from the output here, right? That is well-known test string. And we'll look that one up. I got test string, and you can see there is a Wikipedia page apparently on that. And believe it or not, but it does have a SHA-256 of it. So you don't even need to run your SHA-256 command in Linux or in PowerShell. It's also right here, right? If you want to see what it is, but that would be your submission. So let's come back to this thing. I'm gonna close it. Control-C is gonna probably take some time to actually even close it. It froze my computer for a second. But in any case, the main idea here was to recognize that GitHub quite commonly is full of secrets that you can commonly find on the repositories, official repositories. And those repositories were used to create this account later on I also used an RSA from a random repository on GitHub again, and edit some stuff. Then you just copy this over, you try to brute force it, and there it is. So shoot me an email if you have any further questions or would like to contribute the challenge for our future contests. Take care, guys.